Here's the key for exam number 3, the final video key of the semester. We're asked to provide an IUPAC name for this compound, and we observe there's a carboxylic acid on the right side. So we number starting from that side. We get hexene, or hexanoic acid, I should say. A lot of students had trouble remembering the oic acid part. They called it hexane carboxylic acid. We also have 2 methyls at the 5 position, and we've got these alkene at the 2 to 3 position, which we need to label as E. So the correct answer is E, 5,5 dimethyl hex 2-ene oic acid, or 2-hexene oic acid. So we need the ene, we need that E there to denote the alkene. The oic acid tells us it's carboxylic acid. We need 2 5s because it's dimethyl, and we need the E. If you had all of this here, you got 5 points for this question. If you forgot the E, as most students did, you got 4 points for this question. That's basically because I forgot the E while I was grading it for a period of time and was only reminded by someone who showed me the E. So basically I increased the point value on this question by 1, so this was worth 5 points. The next question is a roadmap question. AlCl3 plus benzene and acyl chloride is simply the acyl benzene. MCPBA, this is going to be the Baeyer-Villiger, given what we have to start with here. If there was an alkene, it might be a different story, but we have just the ketone, and we know that the phenyl ring will migrate before the methyl. And so I make this ester, and of course I can somehow break apart the ester to form phenol. What I was thinking was NaOH followed by acid. Another option is H2SO4 and water, so acid hydrolysis of the ester. And a third option is reduction, where we would basically reduce this carbonyl as far as we can go. We'd lose the OR group and make the phenol. So reduction isn't one way that we really think about isolating the OR group from ester, but it is possible to do that. So 3 options for that box. And then we have phenol, and we're going to nitrate the phenol. Of course, the phenol is an ortho-para directing group, so we put the nitro on the para position, then we reduce it using zinc mercury, and then followed by base, and that gives us the amine off the ring, or the aniline. And then we need to acylate it, so 2 options here, acetyl chloride and pyridine, or acetic anhydride, like we did in the lab. Number 3, we want to write a reasonable arrow pushing mechanism for this reaction, and so we should observe there's only one type of alpha hydrogen. There is a good electrophile right here. Most likely the alpha hydrogen will be our nucleophile, so let's go ahead and draw that. I'm showing the enolate version of this anion, and of course I can show some resonance here. I can use either of these in my next step. So the next step is nucleophilic attack on the aldehyde. That gets me to my 1,3 difunctional group arrangement. And now I can protonate this because we assume there's water around. I made water in the first step, and so I can certainly take some water to protonate here. And of course we are in heat, so we know that we're going to go forward to the dehydration. And I'm going to deprotonate first on this alpha hydrogen. Here's where a lot of students lost a few points here. As you see in the textbook, we need to first stop at this resonance stabilized anion before we kick off the OH. And I need to show that this anion is resonance stabilized. So there's some resonance for that. And then I can reform the carbonyl, form the new alkene, and lose the leaving group to make my final product. So if you didn't show me that resonance stabilized anion, you lost I think, 2 points for this question. So here's our product, and this is an aldol condensation reaction. On to page 2. Which of these is the better choice? So let's look at these. It appears that we are under acidic alcoholic conditions. We want to make an ester here. Certainly this is the conditions to make an ester. That's Fischer esterification. Can anything else happen here? Well, alcoholic acidic conditions could also make an acetal at the ketone or any other carbonyl, aldehyde and ketone carbonyl that's present. So we might get an acetal here. Let's check out the bottom one. We've got one equivalent of sodium hydroxide followed by ethyl bromide. As we've discussed in class, when we add a base, the most acidic hydrogen will be removed, especially if there's a large difference in acidity. So here we have alpha hydrogens, but they have an acidity of around 19 pKa. This OH has an acidity of around 5 pKa, so there's a massive difference between them. There is no way that we would deprotonate any of these hydrogens without first deprotonating this OH, because there's about a 15 pK unit difference. Remember, that's orders of magnitude. So 15 orders of magnitude is a 1 followed by 15 zeros. And that tells you that this is much more acidic right here. And so we would deprotonate this OH. We could add ethyl bromide. That's a good alkylating agent. That's actually a good way to make an ester in this case, and it won't affect anything else. So that tells me that this is probably the better choice. And I could draw this. So I may get some of this. I may get some acetal up here. And this one should work with no problems. And again, a lot of students said, this might happen. And then I said, show me, make the drawing, right? So I asked you to draw. Most of the time a drawing in organic chemistry is more important than just a sentence or two of text. So don't be afraid to draw an answer or draw a partial structure or a molecule to help explain your point. Looking at the second choice, we've got LDA at -78. Definitely going to deprotonate one of these alpha hydrogens. Notice there's no other acidic hydrogens here, so this will definitely deprotonate there. And then we make the enolate in 100%. Propyl bromide probably could alkylate right here and give us the new propyl group. That seems reasonable. Comparing that to down here, sodium hydroxide is not going to quantitatively deprotonate the alpha position. It'll just do it a little bit. Remember that this is an equilibrium condition, so we make some enolate, but we still have a lot of NaOH present. And if I were to add the propyl bromide at that point, I might get a little bit of alkylation, but I might also get some substitution with my OH minus. So I will make that, and a good amount of that probably. So the top one will work. It is 100% deprotonation. This will give us a small amount of deprotonation. And so I'll get a large amount of that 1-propanol, which is not my desired product. So this isn't going to work so well. Moving on to the third option, we've got an aldehyde react with a Grignard. Certainly it can add right there. Let's just confirm that we have enough carbons here. I think some students miscounted and that threw them off. So I have 5 carbons there. So I am adding 2 carbons to the end of my chain. So that's not the issue because I have, of course, a 2-carbon Grignard. Follow that up with acid to protonate the alcohol, and then I can eliminate. That seems reasonable. I'd make an alcohol at carbon 5. I'd eliminate. I could get to carbon 5 to 6. But wouldn't I also eliminate between carbons 4 and 5, making this product? And probably I'd get, I don't see much of a difference between elimination to the left and elimination to the right. There's no steric difference, there's no electronic difference, and so I'll probably get a 50-50 mixture of those 2 elimination products, which doesn't seem very useful. So that's not giving me the top reaction is not looking so good. The bottom one is a 2-carbon Wittig reacting with the aldehyde. It's making the additional 2 carbons, it's making the alkene where the aldehyde was, and it's making the Z alkene. So I think this will work great. I think I'm going to circle the bottom one. The top one also would not give us 100% of the E or Z alkene. We get a mixture of alkenes, and we get a mixture of alkene regioisomers. So we'd have a mess of stuff going on upstairs. Probably if you wrote this little bit that I have here for the third options, you'd get full credit. We get a 50-50 mixture of the 2 alkene regioisomers. You can go on to explain E and Z stereoisomers if you want, but basically this is what I was looking for here. Moving on to the second page, we have just reactions. So let's look at these. Most of these have more than one step to them, so they might be a little more interesting than we're used to. The first one is obviously going to remove the acetal. So we get this compound, the aldehyde, and this is sort of like a stabilized Wittig, right? So we're going to add that to the aldehyde, and we know that a stabilized Wittig gives us the E. And that's pretty cool. That's another way to make an alpha-beta unsaturated carbonyl compound by using a stabilized Wittig. Almost like an aldol reaction, to be honest with you. But this is what we're looking for here. The second question is deprotonation and alkylation. So the first step would give us this compound. And then deprotonation again on the more accessible side should give us alkylation on the left side, and we're adding an ethyl group there. So we would get that species with 2 arms, so to speak, coming out of the 2 alpha positions. Moving on to number 3, we've got very simple conditions here. Most students like that one. That's just an acetal. The SWERN is a way of oxidizing alcohols, and so the first step here is to create benzaldehyde, and in the second step, I hope you recognize from lab, makes the imine. And there is no base catalyst or acid catalyst here because, as we showed in lab, we don't need it. So this would be the final product for this reaction. This one gets into some alpha carbon chemistry. This is a strong base. We've got some alpha hydrogens here. That's really all we have to do. We could add this strong base nucleophile to the carbonyl carbon and make the tetrahedral intermediate, ultimately lose a leaving group, but you'll notice that the leaving group here and what would be the new nucleophile, they're the same. So that's not a productive step. I'm sure it happens, and probably happens many times before we actually deprotonate one of these H's and use it as a nucleophile. And that's okay because again, it's non-productive because we're just swapping the same functional group. So this is a Claisen. It is a little more challenging for students to recognize right after we learned it. So this was not a popular choice on this page. But a Claisen will remove one of these H's and attack another ester, ultimately losing the OR group to create a beta keto ester. So I like to do this by redrawing the original ester. I made a new bond here to the carbonyl, and then I have the rest of the molecule like that, and I've lost the OR group. So here's a beta keto ester. And of course, we know how to do fun chemistry at that doubly alpha position now. Here we have catalytic acid and water and Br2 followed by pyridine, and this is going to brominate on the more substituted side. This is equilibrium conditions, and so we will form the more stable enolate, or enol, that could then attack the bromine. So we're going to make the Br addition at that alpha position, follow that by pyridine, and we get this alpha-beta unsaturated carbonyl species. As some students have pointed out, this is also a dienophile. So we could do Michael additions here, we could do Diels-Alder, or we could do something with the ketone. Here we have a doubly alpha hydrogen. So we're going to deprotonate that, add ethyl bromide. We get to this compound, and then acid and heat and water will create this carboxylic acid, and under high temperatures, meaning close to 100 maybe, not super high temperatures, this is unstable, and actually it will decompose. So let's just draw that decomposition because it's kind of interesting. I have to redraw this a little bit. So we can decompose this to make CO2. And what we do is we transfer that hydrogen, form the CO double bond, the second one that we need, and then we form the unsaturation where we're going to form an enol that can equilibrate back to the carbonyl. And so my intermediate here looks like this. There's CO2. And then this can equilibrate, of course, to that compound. And the end result is that we've added an ethyl group, or any alkyl group that we want, to acetone. Lastly, we have a carboxylic acid with SOCl2. We've seen that many times in class. That makes the acid chloride. We add an excess of amine, and that makes the amide functional group. Next page, propose a product and write a reasonable arrow pushing mechanism for this reaction. We have a lactone, or a cyclic ester. We've got acid, and we've got water. So let's do some fun with acid mechanisms, and let's take the lactone. It's probably going to form into an acid with loss of the OR group, and of course the OR group is still attached because it's a ring. So whenever we're in a fun with acid type problem, you should protonate. Some students forgot that, and that set them on the wrong path, unfortunately, here. I hope that you watch this video and remember that tip on the final exam. So we've protonated the ester now. It's a better electrophile. It can now react with the weak nucleophile water. Then I'm going to make the tetrahedral intermediate. Got a lot of protons flying around here. I'm going to deprotonate the extra hydrogen. How do I know that? How do I know it's time for that? Well, I've got too many on this oxygen here. Plus, I know I want to make the OR group a leaving group, and it's not quite a leaving group yet. Here is where some students drew this, and they lost the leaving group. But you'll notice this is an OR minus, and that's a poor leaving group, especially in acid. So you lost a good deal of credit if you drew this arrow push right here. So let me try to erase that. What we want to do is protonate that leaving group before it leaves. Remember, we're in acid, so everything should be neutral or cationic, and that leaving group is not either of those. Now, we've got our cation here. If we push off the leaving group, we form a neutral leaving group, and that's much more favorable. And now we have the ring has opened. I have the extra hydrogen on the carbonyl. All I need to do is remove that hydrogen, and I'm done with this mechanism. And I can stretch this out. I have 4 carbons and an alcohol at the end. So there's my product here. I've ring opened my ester, creating a carboxylic acid and an alcohol in the same molecule. A lot of you students noticed that this is a good way to make a bifunctional reagent. Now I can do things with the acid on one side, I can do things with the alcohol on the other at different times and make a bifunctional product. All right, on to the synthesis problem. We've got 2 options here. I'm going to work backwards on both of them and then draw the forward synthesis. Let me move these up here. Now remember that the instructions said 5 carbons or less that you can start with, or benzene, but you can start with any monofunctional compound you want to. So we're not restricted to alcohols here, and that was just a time thing because we didn't have a ton of time to spend on this problem. So let's work backwards here. I'm going to switch my colors. Probably the final step here is formation of the acetal from that ketone. We also need to notice that we have meta substitution on this aromatic ring, and currently neither of these 2 groups are meta directors. So we need to have a meta director that ultimately becomes one of these alkyl groups. Now there's a couple ways to make this ketone. My favorite way is to start with this aldehyde and react this 5-carbon Grignard. And of course that fits my rules perfectly because I have just 5 carbons. So 1, 2, 3, 4, 5. And this is a monofunctional group, so I can just buy that. And then I can get to this aldehyde by oxidizing this alcohol. And this is a 2-carbon alcohol added to my aromatic ring. And I can get there by ring opening ethylene oxide. And that is a monofunctional compound that adds only 5 carbons, or adds 5 carbons or less, so I don't need to make that either. And of course, my Grignard comes from the bromine here. Now the question is, how do I get this meta arrangement? Well, this alkyl group could have been an acyl group, and then I can brominate in the meta position and I can reduce that, and of course that can come from benzene. So let's switch colors and look at how we do this. So this would should be AlCl3 and the acetyl chloride. This is Br2FeBr3, and the second step would be zinc, mercury, HCl to reduce the carbonyl. I will point out that a lot of students tried to alkylate this and thus produce the meta arrangement. But of course, this is a deactivated ring. We can't do a Friedel-Crafts alkylation or acylation on a deactivated ring. So that didn't work very well for the beginning. So let me get rid of this. Back to my back to my forward synthesis. I've created my meta arrangement, and I think this is my favorite way to do a meta arrangement because that bromine now allows me to make a Grignard and make any sort of carbon-carbon bond I need to. And so now I'm going to first add magnesium, second add my epoxide, third add H3O plus, and I've got, actually that brings me up here, you get the picture, and now I can oxidize. PCC will oxidize to the aldehyde, then I can mix my Grignard together, and I can follow that up with acid, and I can follow that up with another oxidation to PCC to make my ketone. And then this is just ethanol H2SO4. And so that's how I would make the top reaction, or molecule. Let's look at the bottom molecule a little bit more closely. This is ibuprofen. And how can I make that? There's a couple ways to make that carboxylic acid. I will show you one of them, but I bet you can come up with at least two. If we're careful, we can oxidize that primary alcohol to the carboxylic acid. We probably want to avoid using sodium dichromate or Jones reagent, but we can oxidize this to the aldehyde and then use maybe MCPBA in a Bayer vinegar to make the carboxylic acid. So that's totally doable. We can make that this alcohol through a couple of different means. Some students wanted to use the Grignard to open that epoxide. In fact, I got a ton of students who said, let's do this. But of course, the Grignard will attack at the more substituted side. It'll give us a 3-carbon chain, not a branched chain like we want. So this Grignard will not work. We have to find a different way to make that alcohol. One way, of course, is to add water across that alkene in an anti-Markovnikov fashion. I could make that alkene from this alcohol, and I can make that alcohol from the acetone addition to the Grignard. And I can make the Grignard from bromination and adding magnesium to that aromatic ring. And here's another problem we had. Let me draw my retrosynthetic arrow correctly. A lot of students, they wanted to use that alkyl chloride plus aluminum trichloride and the aromatic ring to add to the group. But this is going to rearrange, forming a cation there and adding T-butyl to the ring. So this isn't going to work either. That's another common error that we saw. And so to make this, to make any sort of randomly shaped alkyl group, you want to put the acyl group on first and then reduce it. So let's look at the forward direction again. We can use the acyl group. Then we can reduce the acyl group, zinc, mercury, HCl, to get our alkyl group on there without rearrangement. Then I can Br2, Fe, Br3 in the para position, add magnesium, and I've got my Grignard. Then I can add acetone to the Grignard. Mild acid workup gives me the alcohol. I can eliminate the alcohol 1, tosyl chloride. A lot of students are forgetting that their alcohol is not a good leaving group. So if you're just adding a base here, you're not going to get the elimination that you want. And then we want elimination, so I'm going to use DBU. There is only one way to eliminate here, so I'm not worried about regiochemistry. Then I need to create the alcohol. That's hydroboration oxidation. And then I am at the alcohol, so I need to oxidize that. I'm going to do a couple of oxidations here. I'm going to do PCC to get the aldehyde. Then I'm going to do MCPBA to make the carboxylic acid. And that's because if I use Na2Cr2O7 acid water, I would possibly oxidize those benzylic positions as well. So I need to be careful here that I don't oxidize those, because those will cut off the chains that I so painstakingly added in this case. Other students used a cyanide nucleophilic attack to add that carbon, and then they hydrolyzed the cyanide up to the alcohol. That was very interesting. Also, other students put a Grignard on that purple dotted carbon, and then they added CO2 to that Grignard, again to add the extra carbon group. So there was many different ways you could have created this, this carboxylic acid functional group. On to the final page. We have X, Y, and Z here. We'll switch back to blue. That we want to identify their structure and make sure that their structure matches the NMR data, matches the formula, and those structures make sense when we look at the reaction conditions. So the first thing we wanted to do was identify the HDI. And so I gave you the formula here because I can never remember how the N plays a role. And so this should have been pretty straightforward for most students. 7 times 2 plus 2 minus 15 plus 1 all over 2. 14 plus 2 is 16, minus 15 is 1. 1 is 2 over 2 equals 1. For Y, we have 7 times 2 plus 2 minus 13 plus 1 all over 2. That equals 14 plus 2 is 16, minus 13 is 3, plus 1 is 4. 4 over 2 is 2. And then we have 10 times 2 plus 2 minus 20. And that's it, we lost the N, so divided by 2, 20 plus 2 is 22, minus 20 is 2, over 2 is 1. So we have 1, 2, and 1 in terms of the HDI. Let's examine some of the NMR data. If you're anything like me, the first set of data looks kind of scary. The second set looks quite interesting and simple, and the third one is kind of in the middle. So I'm going to go with the data for Y. Let me slide this up, get a little more writing room here. All of the NMR datas have this 9 hydrogen singlet here at 0.9 ppm, right where we'd expect a methyl. And of course, 9 hydrogens in a singlet, that implies a T-butyl group. And then I have these two signals, 1.5 2 hydrogen triplet, 2.5 2 hydrogen triplet. And typically when we have two hydrogen triplets and really nothing else, that implies a CH2, kind of a mini chain of 2 CH2s. And then I'm left with the IR signal, 2250, plus the fact that there's 2 HDI and I haven't even accounted for any of them. And if we remember that the IR signal at 2250 or anywhere near 21 to 22 to 2300 is a triple bond. So this could maybe be a CC triple bond, or maybe, remember there's an N here, maybe it's a CN triple bond. And what do I have left if I count my formula, right? I've got 4 carbons here and 2 here, that's 6. I've got 9 H's and 4 H's, that's 13. So I have 1 extra carbon, no extra H's, and an N. So this has to be a CN. And maybe you remember that 22 to 2300 is a CN, or maybe you just did it by process of elimination. But in that case, we've got Y here. That's Y. So that's a nitrile. So let's go back and examine the reactions that this nitrile is going to experience. The Y is going to get a Grignard added to it, followed by acidic workup. So if we do that, we know that the Grignard adds to this carbon, and that makes an imine. Acidic workup turns the imine into a ketone. So that's got to be Z. And if you go back and look at Z's spectral data, you'll agree that it matches up. I don't really have to do that. You'll also agree that Z has just the 1 HDI and that this matches the chemical formula. So I'm going to go back to X and try to figure out what X is. So X reacted with thionyl chloride and pyridine creates Y. We know that Y is the nitrile group. So how do we make nitriles from thionyl chloride and pyridine? Well, if we look at the formula, we actually have 2 extra hydrogens and an extra O. So we have water here. We don't have water over here. And if we look at the NMR, we have the same 9 hydrogen singlet, a couple of triplets. We've got these broad singlets out here. So BR means broad singlet. They're both 1H's. They're out almost in the aromatic region, which is kind of weird. Then for the IR, we've got 1670, which is a shifted carbonyl maybe, or maybe it's a CC double bond, but since there's an O here, it's likely there's a carbonyl. We've got these 2 broad humps and a broad signal at 3000 to 3700. That's often indicative of OH or NHs, and because there's 2 humps, this is probably a NH2. And we know that, so we've got an NH2, we've got these 2 broad signals, those probably are from the NH2. And I have 1 probably carbonyl signal. So let's go back down here where I can draw some. I'm going to add water to this. I know I have an NH situation. I'm not moving the nitrogen anywhere using this SOCl2, but this is starting to look like an amide here. An amide plus SOCl2 will make a nitrile. A nitrile can add a Grignard to make a ketone. This matches the formula. It matches the spectral data. It has just 1 HDI, and of course it matches the reaction conditions. So these are the 3 compounds, X, Y, and Z. And I was very pleased that many students had no problems with this last page. They got the HDI with no problem, and they got these structures with no problem. Finally, the bonus. We are using an amino acid plus this butanone plus acid to make an oxazolidenone and water. And this looks kind of complicated, but if we look carefully, this piece is probably from the butanone, and the rest is from the carboxylic acid. We've got a ketone, we've got an amine, that should tell you that an imine, I-M-I-N-E, will be the first thing that forms. That's the most likely thing because this is the most nucleophilic. We also saw evidence in lab of how easy it was to make an imine. We didn't even add acid. So we may not even need the acid here. I just put it there so that we'd have it to work with. So let's protonate. Let's protonate our ketone. A lot of students tried to protonate the carboxylic acid, but the ketone or the amine is going to be most likely protonated here. And now our amine can attack the ketone. We're going to have a little bit of fun drawing our products, but I have faith that we can handle it. We get this situation. I'm going to transfer my hydrogen, just like I would other times. I'm going to use the ketone to transfer the hydrogen. And again, how did I know that the imine is formed? Well, I observed that we had a ketone and an amine, and that's going to be highly likely to form an imine functional group. And now I'm going to protonate the alcohol so that I can eliminate to make the imine. And now I can lose water. There's a nitrogen right there. And now I'm ready to make the ring. So you'll observe that this carbon here is attached to both the O and the N. Right now it's attached just to the N, but I could take this oxygen and swing it around to attack the N. And actually, I have not drawn this correctly. There's not a lone pair there. There's a hydrogen. That actually makes that N a little more reactive. So probably I'm not going to proton transfer anything. I'm just going to attack that imine carbon and make my ring now. So let's carefully draw this. I'm going to try to draw it similarly to how the product's drawn to help me keep track of everything. And basically that's the product with an extra hydrogen on it. And we just want to be able to confirm all of that. I think that is true. And so I just need to proton transfer that hydrogen away. And that's my product. So we basically form an imine, we leave it protonated. As you can see right here, we form the imine, we leave it protonated, so now it's a better electrophile. It can be attacked by the slightly nucleophilic carboxylic acid on the other side, making a nice 5-membered ring. After removal of this extra hydrogen, we've got our product, the oxazolidenone. And so this was just a fun with acid question, basically forming an imine and then doing one final step.